axes to polar. So what does polar have that's where you could at least sort of locate yourself? Well, polar has the origin, which you don't call the origin, okay? You call it the pole. But it is the point 0, essentially. And then you have what's called the polar axis. Not that you don't have no X and Y axes, okay? You have a polar axis, which is essentially the positive X axis. That's called the polar axis, okay? And then when you have a point P located in the polar coordinate system, you don't give it an X and Y coordinates, you have R theta. So your ordered pair is not an XY, it's an R theta. So what's R? R is the distance of the point P to the origin or the pole. Although it can be negative, but we'll get into that in a moment. But typically it's just for now, just pretend it's always positive. I personally prefer it to be positive. And then the theta is the angle that this line segment, which we'll call OP, makes with the polar axis or the positive x-axis. It's the theta that you probably studied in trig. Okay, so have you guys ever seen polar coordinates graph paper you can buy at the store? You've seen regular graph paper, right? If you buy regular graph paper, it just looks like a bunch of little squares. Have you guys ever seen this kind of graph paper for rectangular graphing? I'm sure you have. It's pretty common, and it's nice to buy it if you're trying to, graph a lot of fun stuff. Well, polar coordinates graphing paper looks totally different. It has concentric circles, so it looks like this. It's kind of cool. Has concentric circles and they call these lines that are coming out of the origin rays like this. It's pretty cool looking. And why is it so cool? Because when you're trying to put a point or plot a point in polar where you're given so if you come down here, let's just do something down here. If you've got your polar coordinate paper and somebody gives you this point, call it P, with the R, which is 2, you go 2 circles away because you get the circle of radius 2. And then pi thirds is the angle that you're making with the polar axis, the positive x-axis, if you will. Okay, so there would be the 0.2 comma pi thirds. And then there's the other examples. You're plotting this point right here with ordered pair 3 because you're 3 circles away, negative pi 6. Now, the thing about polar is that the points do not have a unique representation, unlike XY. Like if you're in a rectangular coordinate system, oh boy, if somebody says, yeah, the 0.23 is an example in rectangular, there's no other way to say the 0.23. The 0.23 is the 0.23 because the 0.32 would be a very different point. But in polar, and you learn this from trig, because you have the idea of angles being what we call coterminal, negative pi 6 is the same as 11 pi 6ths, right? So you can, use one or the other, and they're both okay. So that's legit. Okay. Now I do want to talk about negative R's just to show you, because I guess I don't have an example here. Oh, I'll get to it in another example. Let's wait till the next page. Okay, so let's go to the next page. All right. How do you get from one system to the other? So let's say here's rectangular. This is rectangular right here. And then over here is the polar. Even though technically you're not really supposed to have these X and Y axes, we'll kind of just put them there, place them there so we can locate ourselves. So the point P over here with X and Y coordinates like this, how do you plot the same point over here in polar? How do you get the R? How do you get the theta? So that's kind of weird. So you have to kind of work it from what you know about trig as well as the Pythagorean theorem. And I know some of you could use a little bit of refresher on that because we did some of it at the first week of class, but I just found it was a little bit shaky. So So how do you get from one to the other? And then also, how do you get back again? Okay, so let's say you knew what X and Y are, and you needed R and theta that was the same point. So watch here. You've got, if you drop a perpendicular down here, and then you make a little right triangle. So this is the X, this is the Y. And if you'll notice over here, the R is the length, the distance between P and the origin. So what do you know about Pythagorean theorem? X squared plus Y squared has to be equal to the hypotenuse squared. Oh, okay, cool. So that's one way to get your R. And of course, you're going to square root both sides. So your R would equal plus or minus square root of X squared plus Y squared. But I'm going to choose the plus just because traditionally we like R's that are positive, although they can be negative, as I'll show you in a moment. So then how do you get the theta? Oh boy, how do you get the theta? So where if you only know the X and Y. Well, if you look at this right triangle we have here, what trig function comes to mind if here's your theta and you know what the opposite side length is and you know what the adjacent side length is?
Tangent.
Tangent.
Tangent, good. So write down tangent theta is equal to opposite over adjacent. But for us, tangent theta is y over x. So solve this little mini formula for theta. Well, all I'll do is I'll take arctan or tan inverse, same thing, of both sides of this equation. Okay. And then the left-hand side will be theta, and then I'll have my theta. Now you have to be very careful because of something that we learned back in the first week of class. Do you recall that arctan or tan inverse of x has a range that's restricted from negative pi halves to positive pi halves? Do you guys remember this?
Yes.
You better, because I gave you a lot of like true falses on this, everything. So how the heck do you deal with that? Well, you have to be careful because the answer when you're finding your theta may have to get adjusted. So this works if you're in, negative pi halves to positive pi halves is either in quadrant 4 or quadrant 1. So this formula works only if the point P is in quadrants 1 or 4. Well, what if you're in quadrant 1 or 2 or 3? Don't worry, I'm going to teach you what to do in that case in 2 shakes, all right? But first, let's write this down. So tan theta is equal to y over x, and then theta is equal to arctan y over x, and it works in quadrants 1 and 4 only. Fine. Now, if you were going to go the reverse direction, so basically what I just told you is how to get from here to here. So in this direction, you've got r is square root of x squared plus y squared, and theta is arctan y over x. But how do you go the opposite direction? Like, let's say you already know what the point is in polar, but you need to get back to the world of rectangular. How do you get your x? How do you get your y? So if you recall from your trig days, if you know r, so here's your right triangle again, okay? But you now have different things that you have the info about and different unknowns. So now you know the r, you know the hypotenuse, and you know the theta. Those are the 2 things that you know. What are your unknowns? You need to get your x, which is the side leg down below here, which is the adjacent side leg to your theta, and you need the opposite side leg, the length of y. So you're just going to use trig. So one thing that we know is that cos theta is equal to adjacent over hypotenuse, remember, from trig? So for us, cos theta would be x, which is our unknown, all over the hypotenuse, which is known as r. And if you solve this for x, you get x is equal to r cos theta. And that's how you'd recover your x if you needed it and you knew your r and theta. And similarly, using this same right triangle here, if you needed to recover your y, you use the fact that sine theta is opposite over hypotenuse. So for us, sine theta is y over r. And then when you solve this formula for y, you get y is equal to r sine theta. So boom, a little bit of trig goes a long way. So there's all your coordinate conversion formulas. And for those of you who are taking the time to make a cheat sheet for your final, I'd have this on your cheat sheet, this set of formulas here. Very helpful. So now let's just use these formulas to go back and forth and, you know, convert from either rectangular to polar or polar to rectangular. You need to go back and forth both ways and be comfortable. It's not that hard. Just plug in the formulas. This is way easier than sequences and series, okay? So first plot this point 2, 2, and they're telling you it's rectangular coordinates. So that means they're telling you an X and they're telling you a Y. So you guys know, hey, if you're going to plot the point 2, 2, hey, there it is in rectangular. But what would the same point coordinates be if you were in polar? Well, we know X and we know Y. We need to get R, okay? Well, R is going to be the square root of X squared plus Y squared, which for us is the square root of 2 squared plus 2 squared, but that's square root of 8. And then I always like you to simplify your radicals. Since 8 is the same as 4 times 2, and the square root of 4 is 2, 2 root 2 is going to be your R. Now, what does that give you? Like when you get your R, you know, oh, it's R. Well, it tells you the distance from this point to the pole. The pole is the name of the origin in polar. So that would be 2 root 2. That's all. That's nice. Now, what about your theta? What the heck is the theta? Well, they're asking you to find the angle that this line segment here is making with the positive x-axis. That's all. Like, what's that angle? And since we're in quadrant 1, this formula will work very nicely for us. It'll work perfectly. So theta is going to be arctan of 2 over 2, which for us is arctan of 1. And you should have this one memorized. Does anybody remember arctan of 1? It was on the midterm, I think.
Pi over 4.
Very good. And we're done. And so the polar ordered pair would look like R, comma, theta. And there's your ordered pair in the world of polar coordinates. Any questions so far? It's pretty easy, right?
Yeah.
Okay, now how do you express the same point in different ways? Like, because in polar, a representation isn't unique. Well, you know, we could use the fact that if we went around in the reverse direction like that, that would give that angle is what, -7 pi fourths. In other words, pi fourths is the same as -7 pi fourths. I mean, normally you wouldn't do something like that, but it's still legit. You could go, okay, here's another expression of the same point. Kind of weird, but it's the same guy. It's the same point right here, this point right here. What else? Now here's where R can be negative, so don't freak out. So I'll show you an example where you can have a negative R. So, first you go 5 pi fourths. So what's the angle 5 pi fourths? If you go all the way down this way, there's 5 pi fourths. So you'd find yourself over here in the third quadrant. But then you make your R go negative. So you go the reverse direction. It'll be the same point right here. So that's where R would be negative. Now, again, I do not like at all when my R's are negative. I try to stay away from that kind of representation, but I'm not going to quiz you on it. Don't worry. Like, I'm not interested, but I do want you to know it exists, just so if anybody says, you know, hey, your R could be negative, I don't want you to go, no, it can't, because it can, but who likes that? Nobody. Okay, keep going. Let's go the opposite direction. Let's say they give you the R and the theta, and they want you to come up with the rectangular ordered pair. How do you get that? Now, how would you plot it? Well, you would first try to go 4 units away from the origin. So I'd put myself like right here because that's 4 units away. So I'm right there. But then go an angle of 5 pi 6. Woo! Over here, that's about 5 pi 6, right about there. So it looks like the point that I'm trying to locate in polar would be right there. It's 4 units away from the origin, essentially, or the pole. And it's making an angle of 5 pi 6 with a directed line segment OP, say. All right, How would you get that same point in rectangular? Easy. X is equal to r cos theta. So that's 4 cos 5 pi 6. And this is where you have to remember your trig. And I put a trig unit circle for you in one of your earlier lectures. I think the one on inverse trig. So if you check it and you have access to all of your stuff when you're taking your exam, I think it's negative square root of 3 halves. And then if you reduce this to lowest terms, you get negative 2 square root of 3. And then your y is r sine theta, which is 4 sine 5 pi 6. So that's going to be 4, I think that's a half. Or is it negative a half? No, it's positive a half because we're going up. So it'll be 2. So then when you put this together as an ordered pair, you get negative 2 root 3, comma 2. And there's your ordered pair in the world of rectangular coordinates. Okay? I'm going to skip example 3. It's really easy. Let's do one that the examples 4 and 5, because they're similar, but not really. This is where I'm going to teach you what to do if your point lies in quadrants 2 or 3, okay, to get your theta. It's going to be weird. So first of all, which quadrant are we here with when you graph one? Because they're telling you it's in rectangular. So which quadrant, if I did ask you to plot this point, are we in? 1, 2, 3, or 4?
4.
Good.
4.
Good. So you'd go 1, negative square root of 3. So it looks like it'd be over here. Okay, fine. So so then what? Give me the r, give me the theta. Okay, r is square root of x squared plus y squared. Okay, fine. That's square root of 1 squared. And when I square a negative, it goes positive, so I'm not going to bother putting the negative in there. And then I get 1. Oh, this is nice. Does that always happen? No, but I get a nice number too. Fine. Then theta is arctan of y over x. Be careful you don't do this back asswards, okay? You always want to put the y coordinate on top and the x coordinate below. Otherwise, you'll get into trouble and you'll have the wrong angle. Okay, now I don't know what this is off the top of my head. So what I do is I crack open my, my graphing calculator and I make sure that I'm in degrees mode, and then I convert it to radians if I can in my head. But it turns out that when you, and so this one, just so you remember how to do arctan, this takes a while for my TI-84 to come up because I think it takes up a lot of memory in my, wow. The last time I was trying to use this, I got stuck in a mode. Yeah, it's not working. Huh. This is so weird. Huh. Yeah, it's almost like it's hosed, like I'm stuck. Oh, RAM cleared. Oh. I got minus 60. Yeah. No, I know what the answer is. I just don't know why I'm not getting, okay, here we go. Now it looks like it had to reset itself. That's one thing I learned as an engineer, always reset. So if I go into degree mode here, let's see if it's going to work now, and then hit enter. Okay. And then quit out of here. And let's see if I can do an arctan just for kicks and giggles. And I go, okay, negative square root of 3 and divided by 1. So I don't really care about that. So just hit it. Oops, it doesn't want. Okay, let's see what happens. Negative 60 degrees. Yep. Okay, fine. So then what? Well, negative 60, I believe, is negative pi thirds. So you're like, okay, what's the final answer? Our final answer when we put this together as r comma theta is going to be 2 comma negative pi thirds. Fine. And you're good. So so now what? Well, what if somebody said, hey, look at this point, where are we located here? Actually, let me go back to example 3. Let's do example 3. Which quadrant are we in here? No, sorry, that's already in our theta. Yeah, this is where? Negative 5, negative 2, quadrant 3. Yeah?
Yes.
So if somebody said, okay, convert to polar, you're going to go, okay, you'll get some weird number here. Ooh, this is not going to be a pretty number. That's okay. Square root of 29. We're going to go with it. And then theta is going to be arctan of -2 over -5, but negative divided by negative is a positive. And my calculator says 21.8 degrees. Okay, do you guys get that that's wrong? Like if you graph -5, -2, okay, it's like somewhere over here. Does it look like, if I create this line segment here, does this angle here look like 21.8 degrees to you? Please say no. I don't think so. Bummer. So anytime you're in quadrant 2 or quadrant 3, after using your graphing calculator, add pi radians or 180 degrees, and then you'll get the correct answer. Okay, so that's the trick. And this ends up being, I believe, 201.8 degrees, and we'll leave it in degrees, even though technically it would be nicer if we put it back in radians, but I'll leave it. Okay, and we're done with points. Okay, now, folks, what we've just done in the last half an hour is just an intro to polar. So just to recap, now you just know how to go back and forth between the Cartesian coordinate system, which is known as rectangular also, and go to polar or back, and with points. But usually we don't deal with points because they're not interesting. What are we usually interested in? Well, just like when you were in algebra and pre-calc, you were interested in graphing lots of points and connecting them together, like graphs of functions. Yeah, that's what we were interested in, not just singular points here and there. That's boring. So let's look at graphing polar equations. So that's next up. We're still not ready for the calculus yet. We're going to do that on Friday. But we'll talk about how to graph polar equations. So you've studied equations in rectangular form, like y equals x squared or whatever. But what about polar? And so this is kind of fun. And I'm going to teach you how to do this on your graphing calculator. So, I should probably whip it out again. Oh, man. Sorry, I closed it out. Okay. So if you're going to graph some polar equations, let's graph one of the most easiest of all. And this one, you don't even really need a graphing calculator to graph. R equals 3. What is that telling you? Graph all the points that live 3 units away from the pole, no matter what their angle. We don't even care what the angle would be. And it turns out when you graph all the points that have 3 units away from the pole, you get a perfect circle centered at the origin of radius 3. That's right. And so prove it. So to do polar in your graphing calculator, first click on the mode key and then see where it says function. And before we were graphing in parametric, what you want to do is go down to that row that says function and move your cursor over to the word polar. And then what you can do is click enter to choose it and then cancel or then quit out of here. And then when you hit your y equals button, it will ask for r equals. And so you give it some function of theta. Well, r equals 3 is what we need to graph right now. And then check your window. Let's graph it from theta min 0 and 6.28 is 2 pi. So when you go to your theta max, do 2 pi because then you'll get the full complete picture. And then when you hit your graph button, cool. And nothing happened. Oh, I know why nothing happened. It's not because my calculator is broken. I forgot to get into radians mode. Remember when you graph trig kind of stuff, you need to be in radians mode. Otherwise, it looks like your calculator is broken. Yeah. So make sure you're back in radians mode and then graph it. And it looks like an ellipse, but that's just because of the nature of your screen. If you go into Zoom and click Z square, it'll kind of square up your screen there on the display, and you see you have a perfect circle centered at the origin. So R equals a pure number is always going to give you a circle centered at the origin of whatever radius it is. And that's kind of good to know for polar. Now, how would you convert to rectangular? Well, you could just use your knowledge of circles, but if you use the conversion formulas, remember that r is the same as square root of x squared plus y squared. And then when you square both sides, you get that. And that is the same as a circle centered at the origin of radius 3. So this is the rectangular equation that's the same. Questions? Everybody okay? Okay, now let's try to graph something that you can't use your graphing calculator for. Why? Wait a minute, you just told us that we can use our graphing calculator for graphing and polar. I lied. It has to be where R is a function of theta. And here we have theta is a function of something. So only your calculator only works for R equals functions of theta. Anything else can't do it. And this should make sense to you because when you are in function mode, your calculator is also very limited and that it only allows you to graph y equals functions of x, right? I mean, you couldn't graph x equals y squared minus sine y plus 17y, could you? Using your graphing calculator? Not only no, but hell no, because that's a function of y, not a function of x. You guys with me?
Yeah.
Now, I do want to say that if somebody said, try and graph this, you now know how to do it. Does anybody want to take a gander at how you would do this? See if you were focusing up last week. If not, it's okay. I'm just seeing if anybody out there knows it. Anybody want to go for it?
You can separate it into parametric equations.
Lisa, God bless you. You're awesome. Okay, yes, parametric. Convert to parametric. You're awesome. Okay, help me do it. So since this is a function of y, who gets to be equal to t? So I need x equals and y equals, where x is going to be a function of t, right? And y will also be some function of t. Yes? So which one? You want to try, Lisa? Very good. And then x would be?
T squared minus sine t plus 17t.
You guessed it. Very good. Yeah, so you could graph that now that you know how to do parametric mode. Very good. I'm not going to do that, but I'm just telling you. So over here, how would you graph that? Well, it's basically saying the set of all points that are exactly pi-4ths radians away from the polar axis. So here's the polar axis right here. So what are all the points that you can think of that have an angle of pi-4? So it would be all the points that, you know, right here. But remember, because R could be negative, it's going to be these points over here also. Okay. And so if I connect all those dots, it's going to be basically a diagonal line looking like that. Well, I would never have known that. Well, let's say somebody said convert to rectangular. So what would I do to convert this equation to a rectangular equation? Well, this is the trick. Let me rewrite the equation. Theta equals pi-4. Fine. Take tangent of both sides. Well, why the heck do you want me to do that? Hang on a minute. I'm going to show you why. Because if you go back to your conversion formulas way back here, do you remember that tangent theta is the same as y over x? Yeah. So by taking tangent theta of both sides of this equation, I now can replace the left-hand side with y over x. Then what? Well, tangent of pi-4 is just some funky number. Anybody want to tell me what it is?
Isn't it 1?
Yeah. And then you're pretty much done. There's the rectangular equation. But if you really want to make it look prettier, multiply both sides of the equation by x, and y equals x is the rectangular equation. And sure enough, this graph right here is exactly the graph of y equals x. So there you go. All right. Now, how about r equals 2 cos theta? Okay. So if you go to your graphing calculator, let's have some fun and go to y equals. Let's clear this out and graph 2 cos theta, okay? And I think the window 0 to 2 pi, let's just do 0 to pi to see what happens. If I make my theta maximum just pi, what would happen? Ooh, I don't need 2 pi. I get the full picture without it. So I only need 0 to pi. And it's a tiny, tiny circle. Let me just zoom in a bit because it's almost disappearing. Let me do a zoom in. There we go. So it's a circle that's not centered at the origin. Ooh, cool. So there it is. And it only needed 0 to pi to sketch the whole thing. Very nice. Now, how would you convert this to rectangular? This is a little bit tricky. And for those of you who took trig, I'm hoping that you saw this already in a trig class, because when I teach trig, I go over this. I haven't taught trig in like almost 20 years, but it's been a while. But I still have all my lecture notes. Okay, so the trick is you're going to do something that's typically illegal, which is multiply both sides of the equation by a variable. So you're going to multiply both sides by r. Now, why is that typically illegal in a mathematical maneuver? Does anybody want to tell me why mathematically, all you math majors out there? Check the chat. Why is it illegal to multiply both sides by a variable typically? Like if you had, let's just say you had 2 over x, I'm just making something up, plus 1 is equal to 17x. Just say, even though most of the time you think, oh, what's the problem? I'm going to multiply both sides of this equation by x. What could go wrong? Why could this be very illegal mathematically?
Because it could be 0.
Thank you. Exactly right. Bingo dingo. And you're not allowed to multiply both sides of an equation by 0, which is kind of obvious. So I'm going to do something kind of illegal. Well, you just got done saying it's illegal. How dare you? You're a hypocrite. No, I'm not. I'm going to assume that r isn't 0, and I'll be safe. And then further, I can say that we're actually going to pick up. Usually when you multiply both sides by a variable, it may, or divide by a variable, when it could be zeros, you may lose information or something. We're not going to lose information. So if I multiply both sides of this equation by r, the left-hand side will be r times r, which is r squared. And on the right-hand side, we'll have 2r cos theta. Well, how is that helpful? This is like terrible. No. It made it easier for me to use my conversion formulas now. Because if you look at r cos theta, what can I replace r cos theta with? Go back and look at your conversion formulas I put on the first page. What's r cos theta the same as? Quick.
X.
Yes, it's x. So if you look here at this box, remember that x is r cos. So it's like, oh, cool. So now by doing that little tricky poo, I can replace the r cos theta with x. So the right-hand side is going to be 2x. And the left-hand side, what do I replace r squared with? Anybody know? Okay, I'm going to call on people. Alec, are you still in the room? Ortega?
Yes, I am.
What's r squared equal to? Just go check your formulas there.
X squared plus y squared.
Yeah, that's exactly right. Thank you. Okay, so we're going to have x squared plus y squared. And we're pretty much done. You just converted to a rectangular equation. And does that guy's graph have the same look? Like it looked like there's this little circle right over here. And is that graph match? Well, it does, because if I told you, we'll go further and prove that circle not centered at the origin is the same guy. If I move the 2x to the left-hand side like this, and then I complete the square, and you did this already in pre-calc, I know you did, by adding a magical mystery number there that will make it a perfect square, and we'll add the same magical mystery number to the other side of the equation. And remember, m, I taught you how to complete the square like the first week of class, is the middle coefficient divided by 2 squared. So I claim it's 1. So if you complete your square there, and don't forget to add that same number to the right-hand side, then this is a perfect square trinomial. That's the whole point of completing the square, which means it factors as something squared, right? Anybody want to tell me what that factors as?
X minus 1.
Good. Does everybody see that this is a circle of oh boy, I hate PDF annotate. Please, come on. Well, it didn't want to do it. Take. Okay, fine. This is a circle. I'll just make an arrow pointing to it. Is a circle of radius 1, where the center is 1, 0. Do you remember that standard equation of a circle formula from pre-calc days?
Yeah.
Okay, so in other words, if you look at what we graphed here, the circle is right there at 1, 0, and it does look like it has a radius of 1. So yes, it matches, so it's the same. Now I'm going to do a hard one, which is in my math lab. This one's hard. So what if somebody said, hey, try to rewrite that puppy as, well, graph it first, and then try to rewrite it in rectangular. And this one's a little bit tricky, but here's the first thing you got to do. If you're going to use your graphing calculator to graph it, you're going to first need to divide by cos theta, because you need r to be a function of theta. So if you do that first, then you're able to use your graphing calculator to actually graph that puppy. So if I go over here to graph it, go to y equals, and let's clear this out. And then I go sine 2 theta divided by cos theta. Heck, what the heck does that look like? I don't even know. Whoa, it's another circle. Very cool. And it doesn't look like it's centered at the origin either. Okay, fine. So then what? Well, how do you come up with the corresponding rectangular equation? So if you go back here, and if you're going to work it, you're first going to use a trig identity. What trig identity? It's a double angle formula that says sine of 2 theta is the same as 2 sine theta cos theta. Does everybody remember that? Hello?
Yeah.
Yes.
So if I leave the cos theta on the other side and I replace the right-hand side with that trig identity, if once I divide by cos theta, and we'll assume cos theta isn't 0, otherwise we're going to be screwed if we try this, the cos thetas cancel and we just get 2 sine theta. Okay, so that's fine. Then what? Convert that to rectangular. So I'm going to do the same trick, and the trick is multiply both sides of the equation by r again, you know, and then r sine theta gets replaced with what conversion formula?
Y?
Mm-hmm. So that's your y, and you got a 2 over there, and then this is x squared plus y squared, and you can call it a day right there. Okay? And you get a circle not centered at the origin. And you can go do the complete the square thing if you need to, and you'll see it's a circle centered at 0, 1 of radius 1. Okay. So those are fun and fine, but they're not very interesting because we just graph a whole bunch of circles. That was boring. Now, what about some really fun times? Because polar graphs can be really amazing. So let's look at a few. How about 3 sine 4 theta? You probably did not do this in a trig class, okay? But you're going to do it here. And we're going to do calculus on one of these puppies. So what do I mean? Well, you know, go back to your graphing calculator, clear out this business, and try graphing 3 sine 4 theta. And I'm going to have my window go from 0 to 2 pi because I think I need 2 pi to pick up the whole picture of this graph. It's really cool. Check it out. Whoa, that looks amazing. What do you guys think? Doesn't that look pretty?
It's really cool.
I mean, come on. You guys should be duly impressed. What's wrong with you? Well, anyway, okay. So you get a really nice picture. That's called a rose curve, by the way. That's a rose curve, and it's pretty cool. And so try drawing that on your paper. I don't know if you're good at drawing. Yeah. Woo, 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 woo. It's a rose curve. Okay, beautiful. Okay, fine. What's another weird looking polar graph that, woohoo! Letter B, this one's interesting. 1 plus 2 cos theta. Okay, fine. What do we got? What do we got? Let's clear out the beautiful flower. Okay. And we'll go 1 plus 2 cos theta. And we'll leave it from 0 to 2 pi. I think that will graph the whole thing. Oh my goodness, wasn't that cool? Did you see that loop-de-loop happen? Now that is awesome. So it's a loop inside of a loop, which is way cool. Let's see if I can draw this. It's got like a little loop there, and then it's got an outer loop and an inner loop. Okay, that's fun. Aren't you guys impressed with that one? I mean, you should be. It's kind of pretty. And then a half theta. This one's way cool. I love this one. Let's clear this out. If I go r equals 0.5, that's a half theta. Here, I can let my thing go from 0 to 2 pi, and then it just kind of looks like a snail shell. But if you let your window go from negative to positive, check this out, have your theta minimum be -10, and then let your theta max be +10. Check this out, checker outers. It's going to spiral in and then spiral back out. It's awesome. Okay, don't blink because it's going to go quick. Whoa! Let me do a zoom out on that so you can appreciate the beauty. Let me do zoom standard. There we go. There we go. I went back to a terrible window. Oh, see, I guess the default window. Let me go back to -10 to +10 and pick up that full spiral in and spiral back out. Awesome sauce. That looks lovely, doesn't it? I mean, come on, people. You should be excited. Those are fun. So that one, I don't know if you can draw like a spiral in, spiral back out. Forget it. Whatever. Okay. There is another graph that I'd like you to see while you're here. Try looking at 2, 1 minus sine theta here real quick. Watch what that one looks like. Oh, shoot. 2 parentheses 1. So, oh my God, sine theta. Okay, when you graph this, it doesn't have a loop-de-loop. I like to think of this as sort of a circle with a little bit of butt cheeks to it, okay? You know, butt cheeks, right? Sure. How do you draw that? Oh, that's weird. Okay. You know, for those of you who really like graphs, you know, if you're really excited by graphs, let me just show you a quick demo of all the things that you can do with, you know, graphing. So here, like, you know, that's just cosine X, which is boring, which, you know, who cares about that? And this, by the way, this software you can buy online. It's by Pacific Tech. You can draw, you can sketch things in polar as well as rectangular. Now this is rectangular, which isn't very interesting, but then you can also graph things in 3 dimensions, which you're going to be doing in Calc 3. Like this surface right here, z equals xy. Oh yeah, you're going to be doing that in Calc 3. Get excited, people. And then of course you can graph, you know, boring stuff like, you know, mx plus b. Who cares about that? You know, it's like, yeah, okay, y equals x squared. Who cares? And, you know, or, you know, something like that, you know, an exponential equation. Oh, it looked like I accidentally stopped the demo. Hold on a second. So let me go into, just show you something here. So that's y equals e sine of x. Here's nx, and this is where n can be variable. So if you have sine 2x, 3x, or whatever, ooh, that's sine of e to an exponential. There is another exponential involved where x sine of 1 over x or whatever. X equals y squared. This software, you can graph functions of y, which is way cool. There is r equals 2. You guys know that. I just showed you. Ooh, there's one of those 2 cos 2 thetas. There's the spiral. Here's a function of r. There's a circle. That's boring. That's an ellipse. Ooh, that's a cool graph right there. This is another polar coordinates. Now right here, they're doing something called parametric. There's parametric stuff. There's another parametric with r and theta. There's some more fun graphs for you. Ooh, there's some more fun graphs. Oh my God, that's exciting. That's parametric equations in 3D right there. Another 3D parametric. You'll do that in Calc 3. Another 3D that's where you have spherical coordinates. And spherical coordinates are 3D coordinate system you'll learn in Calc 3. So stick around, come to Calc 3. This is an inequality in polar. Oh my God, look at that, people. Oh, that's awesome. Oh, ooh, that is even more awesome. This is a vector field. You'll learn about vector fields in Calc 3. So definitely come to Calc 3. Ooh, check that out. That is just awesome sauce, man. That is another polar inequality, people, polar inequality. Okay, so you can do a lot of really cool stuff in polar, and this is one of them right here. Okay, so enough said about that. Let me bomb out of that. Okay, so I don't know if you're excited about polar or alternate coordinate systems, or maybe you're getting excited about Calc 3. Either way, it's all good. So let's do a little bit more here. How do you graph equations in rectangular and then convert to polar? So let's go the opposite direction. This is a circle not centered at the origin. So if you had to complete the square and do all that, you could figure out where it's centered. But here, it's quicker to do it in polar. Check it out. X squared plus y squared, convert it to polar. You replace it with r squared. Minus 4y, but y is r sine theta. And you're pretty much done, although my math lab won't give you full credit, because here's the extra steps you need to do. Add 4r sine theta to both sides, and then do something that's typically illegal in math. Why? Dividing both sides by a variable, not good. You could be dividing by 0, but we'll assume r is not 0. And then you'll have r equals 4 sine theta. And there you go. So if you go back to your graphing calculator and you graph 4 sine theta, oops, I have too much other stuff on here, 4 sine theta should be a circle not centered at the origin. And there it is, okay? So it looks something like that. And then how about xy equals 4? How would you convert that to polar? Well, again, by brute force, you replace x with r cos, you replace y with r sine, and you're pretty much done. Although typically they like you to solve it for r. So the way you could do this is you would divide both sides by cos theta sine theta, and then you would take the square root of both sides, and you would get plus or minus square root of 4 over cos theta sine theta. If you wanted to clean this up a little bit, since square root of 4 is 2, you could just rewrite it like this, okay? And then you could definitely graph that. I think it's going to be, what the heck is that going to be looking like? Well, xy equals 4 is y equals 4 over x. So this will look something like this. And then finally, y equals 5, which everybody in the room knows is a horizontal line. But if you had to convert to polar, you would just replace y with r sine theta. That equals 5. And then if you rewrote it where r is written as a function of theta, it would look like 5 over sine theta, which is the same as 5 cosecant theta. Okay? So I think that's a really good place to quit as far as, you know, I wanted to show you a fun meme though before I finish the class. So here's your meme. This is the Cartesian bear. You know, he's in X and Y coordinates where everything is kind of squared up and your graph paper is a bunch of squares. And then your polar bear, ha ha, ha ha ha. You're supposed to laugh. Come on, that's the only meme that I could find. I looked everywhere. I looked everywhere for a meme on polar. It's not hard to find. So what do I do with this information? Well, nothing right now. Just know that there are all kinds of cool graphs out there, besides all the boring ones that you've been working with all these years. There's a whole new vista out there. And you can do calculus on that stuff. And the calculus would be finding slopes of tangent lines. We're going to do that next time. Finding points of horizontal and vertical tangency. And then in polar, we're going to look at finding polar area. So just to let you know what's coming up briefly or quickly for you, besides my little quick meme there, which I know is really cute. I love polar bears. So like, look at this example right here. Just take a look here. What if somebody picked a point on there and said, hey, what if I draw a tangent line? What's the slope? of that tangent line to a point on the polar graph. So that's what we're going to figure out slope next time. Arc length. You remember arc length, people? You already know how to do two versions of arc length for functions of X or Y, and then the parametric form for arc length. There's another arc length. Like what if somebody said, hey, I want you to find the arc length between here and I don't know, over here on a polar graph. Go get it. There's a formula for it. And then further, this is really fun. We're going to do area in polar. And this is what they do in Calc 3. Like what if somebody said, hey, I want the area of just the inner loop. You remember this was a loop-de-loop? It's an inside loop inside of an outer loop. Go find the area of the inner loop only. Go. How do you do that? Well, I'm going to show you how on Friday. Okay. It'll be kind of fun. So something to look forward to. I'm pretty much done. I don't really have office hours today, but I will stick around after class for any last minute questions or anything that you'd like to talk about. Otherwise, I'm done. See ya. Have a good day. Remember your homework. Go kiss your mom. Go kiss your dad. Okay.